Okay, 5.11, we're going to solve optimization problems. Optimization normally involves finding a minimum or maximum value and where it occurs. We set some of these up last section, but now we're actually going to solve them. So the strategies for solving optimization problems. We draw a picture, if applicable. We write an equation relating the variables. We write an equation for what's being optimized. We write the equation in terms of one variable. We find the critical numbers by finding the first derivative and setting it equal to 0 or does not exist. We check critical numbers endpoints to verify if they represent maximums or minimums and answer the question. Let's start with example 1. Example 1, a particle is traveling along the x-axis and its position from the origin can be modeled by this function, where x is centimeters and t is seconds. On the interval 3 is less than or equal to t is less than or equal to 9, when is the particle furthest to the right? Okay, we want furthest to the right. The equation they gave me is the equation for the position of x, so we want the maximum x value, which is why this is an optimization problem. I already have the equation I need to optimize, so I'm going to go ahead and find my critical numbers by using the first derivative. So first derivative of x prime of t equals 3t squared minus 30t plus 72. Let's find the critical numbers by setting this equal to 0. I'm going to take out the 3 since I can see that everything is divisible. Okay, t equals 6 and t equals 4 are my critical numbers. They want furthest right, they want an absolute maximum. Since they want the absolute maximum, I'm going to use the extreme value theorem. I'm going to check the endpoints and the critical numbers to see which produces the maximum value. Okay, so the critical numbers are 6 and 4, so I'm going to do x of 6 and x of 4, and then the endpoints are 3 and 9. It says it can equal them, and that's normally the hint that it's going to be the extreme value theorem. Okay, so this is my x function. Looks like this. I'm going to go ahead and plug each of these values in. I don't want to have to retype it, so I'm probably going to use the table function on my calculator, or I'm going to save the equation. Okay, so these are the values I get out of these functions. So x of 6 is 99, x of 4 is 103, x of 3 is 99, and x of 9 is 153. I am looking for the absolute maximum x value. So this is my answer. If it asks me to justify, this is my justification. So now let me answer the question. It says, when is the particle furthest to the right? Oh, so they want to know when. When is the seconds? The seconds are time. So the answer is at t equals 9 seconds. This is the answer to when the particle is furthest to the right. But I had to show this step to justify that I checked for the absolute maximum x value. Okay, for part B, on the interval 3 is less than or equal to t is less than or equal to 9, what is the particle's maximum speed? Okay, let's think about this because they're talking about speed. They're not talking about velocity. What is the speed? Okay, let's see. I know that speed is the absolute value of the velocity. So let's start thinking about the maximum velocity, and then I can figure out which one's going to give me the maximum speed. What's the equation for velocity? They didn't give me velocity, they gave me the position. But the equation for velocity is the first derivative of position. So the velocity equation is actually this one. Okay, if I want to maximize the velocity, I need to take the derivative of the velocity to find the critical numbers. Okay, let's set this equal to 0 and then solve for t. T is 5. So this is the critical number for the maximum velocity. And I'm going to use that to get the maximum speed. Okay, since I want the absolute maximum, I want to check my critical numbers velocity. And then I also want to check the endpoints, which are at 3 and 9. Okay, now this is going to tell me the maximum velocity. I actually want the maximum speed. So since speed is the absolute value of velocity, let's go ahead and absolute value these answers and see which one is the maximum. Okay, so if I plug 5 into the velocity equation, which is this one, no, it's not, it's this one, and I would use my calculator again because I don't want to have to retype it. V of 5 is -3, but I'm going to absolute value the -3, so the velocity is -3, but the speed is 3. Okay, I'm going to plug in 3. The velocity is 9, but when I absolute value, I get 9, and then when I plug in 9, I get 45, the absolute value of which is 45. Okay, this is my work for using the extreme value theorem. Let me answer the question. What is the particle's maximum speed? Well, the actual maximum speed was this one. So max speed is 45, and what were these units? Centimeters per second. Okay, so I answered the question, but I did have to show the work to justify my answer. Okay, let's look at example 2, which is more like a typical optimization problem. It says find two numbers whose sum is 10 and whose product is as large as possible. Okay, I might try to draw a picture, but there's no picture to draw here. So let's write in the equations. Two numbers whose sum is 10. Let's pick two letters. Sum is plus, so x plus y is 10, and that's because sum is plus. What am I trying to maximize or minimize? It says they want the product to be as large as possible. Product is time. Product is times the two numbers. I want them to be maximized. So I'm trying to maximize the product. So I need my equation to be for p, so I can take the derivative of p and find p prime, because maximizing profit. Okay, let me solve this equation for x or y, the first one. It doesn't matter which one you choose. Okay, if y is 10 minus x, let's plug in 10 minus x. Okay, I'm going to have to do p prime. If you would like to do the product rule and do it here, you can do it here. If you would like to simplify it first, you can simplify it first. I'm going to simplify it first. Okay, so that's my equation for product. I want to maximize the product, so I have to do p prime. Okay, and to find the critical numbers, I'm going to set this equal to 0. Okay, so I got that x is 5, and there's a critical number. I don't know if x is 5 produces a minimum or maximum, so I need to verify. You can use the first derivative test or the second derivative test. I'm going to use the first derivative test. So on my number line, I'm going to do 5. I'm going to plug 5 in, the numbers below and above 5 into p prime to see if this is a relative minimum or maximum. Okay, let me pick a number lower than 5. How about 0? I'm plugging it into p prime. So 10 minus 0, positive. If I pick a number higher than 5, like 6, 10 minus 12 is negative. It says p prime is going from positive to negative. 5 is going to represent a relative maximum, or the location of a relative maximum. Am I looking for a maximum? I am looking for a maximum. I'm looking for a relative maximum, or the absolute maximum. Since there is only one critical number and that represents a relative maximum, this is actually also the absolute maximum. So what are the two numbers? I know that x is 5. What's y? Let me plug it in. 5 plus y equals 10. Y is also 5. So then answer the question. What are the, find two numbers whose sum is 10, 5 and 5, and whose product is as large as possible, which is 25. Okay, example 2 was like the warm-up problem. Now let's do some real problems. Okay, for example 3, what point on y equals square root x is closest to 5, 0? We set this up last class. So let's pick a point on here. I'm picking an arbitrary point to see if this is closest. What is this point down here? This is 5 to 0. I want the distance from this point to minimize. So I want to minimize d. Okay, let's write an equation for d. D is the distance from xy to 5, 0. So let's use the distance formula. Distance formula is subtract the x's and square them. subtract the y's and square them. Okay, and then because I want to make this all into one equation, I'm going to plug y equals square root x, square root x in for y, so I can simplify the equation. And since the minus 0 doesn't matter, I'm going to ignore it. Let's see. Okay, now I'm going to have to take the derivative of this at some point, so I'm going to simplify this because I think it's going to make it easier for me. The square root of x squared is just going to be x. Okay, so I found an equation for d in terms of one variable. That variable is x. Okay, now to find the critical numbers, to minimize d, I need to find d prime. So d prime equals, since this is square root, the exponent is 1/2, so let me bring down the 1/2. And I'm going to lower it to the negative 1/2, and then because of the chain rule, I need to multiply by the derivative of the parentheses, which is going to be times 2x minus 9 equals, let's see if we can make this look any better. 2 is at the bottom. The square root of x squared minus 9x plus 25 is in the radical. And if you had not simplified this much, we should have an equivalent answer, and that's fine. Okay, so now I need to set this equal to 0, and I need to figure out when it doesn't exist so I can find the critical numbers. Okay, if I set d prime equal to 0, the bottom's going to cancel, so it's really just the top equaling to 0, which means x equals 9/2. That's my first critical number. If I look at the equation, as long as this is positive, it's going to work out. I'm pretty sure it's positive. Okay, now let's see when d prime does not exist. For it to not exist, the bottom has to equal to 0. So let's set the bottom equal to 0. Okay, if I divide by 2, it goes to 0. If I square both sides, it goes to 0. So I'm going to end up with x squared minus 9x plus 25 equals 0. Okay, now I would love to factor this, but it does not factor because 5 times 5 is 25, and that adds up to 10. So I'm going to quadratic formula this or complete this square. What is that? B squared 81 minus 4ac 100, which is 9 plus or minus root negative 19/2. Yeah, I'm going to get an imaginary number. So this does not count as a critical number because there's no real solution here. So we only have one critical number. Hopefully that critical number is a minimum, but we need to verify that it is in fact a minimum. So I'm going to make my number line. I'm going to put 9/2, and I'm going to check the sign of d prime. Okay, let me pick a number below 9/2. It's easy. I'm going to plug in 0. I'm plugging it into d prime, which is here. So if I plug in 0, I get, at the top, I get negative 9. At the bottom, I get 2 times the square root of 25, which is positive. So that's going to give me a negative here. Let's plug in a number higher than 9/2. How about like 100? How about 10? 20 minus 9 is positive. On the bottom, if I plug in 10, that's 100 minus 90. 10 plus 20, that's positive. That's positive. Okay, since d prime changes from negative to positive, this is proving that there is a relative minimum. If they asked me to justify it, I would say there's a relative minimum at x equals 9/2 because d prime changed from negative to positive. So now what is the question asking me to find? What point on y equals square root x is closest to 5, 0? Okay, so this is the x value. The y value, I need to plug x into y equals square root x. So I'm going to get y equals square root of 9/2, which is 3/√2. And am I going to rationalize that? No. You're welcome to do so, but it's not going to make it a better answer. Okay, last example, and it is a calculator active problem. Same setup as last time, but I'll remind you of the setup. 2 towers are 30 feet apart. Okay, tower to tower, 30 feet. One is 12 feet high and the other one is 28 feet high. So 12 foot tall, 28. And it doesn't matter which one's on which side, at the end we will have the same answer. There's a stake on the ground between the two towers. It doesn't say it's in the middle, it's just somewhere in there. The top of each tower has a wire tied to it that connects the stake to the ground. Top to stake, top to stake. The green is the wire. Where should the stake be placed to use the least amount of wire? Okay, so I'm going to call this Y and call this Z. So the wire is going to be the distance of Y plus Z, and I want to least amount of wire. I want to minimize the wire. Okay, now I need to get this Y and Z equation into one variable. Okay, so unfortunately I'm going to introduce a new variable. I'm going to just go ahead and put an X here. If this is X, then this is 30 minus X. You could do this vice versa. It's not going to make a difference. Okay, so the way I have this set up, I'm going to have X squared plus 12 squared equals Y squared. If I solve for Y, I get the square root of X squared plus 12 squared, or 144 if you like. If I do this second equation, I get 30 minus X squared plus 28 squared equals Z squared. So Z equals the square root of 30 minus X squared plus 28 squared. Okay, now let me rewrite my equation in terms of X. So for Y, I have X squared plus 12 squared. And then for Z, I have the square root of 30 minus X squared plus 28 squared. Okay, now that I have the equation for W, I want to find W prime. This is calculator active, but most of your calculators are not going to find W prime for you. A couple of your calculators might. Okay, so I need to take the derivative. It's going to be terrible and ugly, but then to find the critical number, I am going to use my calculator. Okay, so W prime, and I could definitely simplify this, but I think it's going to be bad no matter what, so I'm going to leave it. If this is, the exponent is 1/2, so I'm going to bring down the 1/2. It's going to be X, it's going to be to the negative 1/2, so I'm going to go ahead and just move this to the bottom. If you would like to make that 144, you can. If you would like to leave it 12 squared, you can. It's not going to make a difference. It's just a matter of typing. Okay, then because of the chain rule, I am going to times by 2x. Okay, and then the next one's going to be similar. It's raised to the 1/2, so now it's the 1/2. And it's negative 1/2, so it's going to move to the bottom. If you want to do 28 squared, you can. I don't know it off the top of my head, so I'm not going to. If you want to times this out, you can also. Since I don't know it off the top of my head, I'm going to use the chain rule to do the derivative. So I'm going to do the derivative of this. I'm going to bring down the 2. Lower it to a 1, but then I have to do the chain rule again because the derivative of 30 minus x is negative 1. Had I distributed it out, I wouldn't have had to do all that. Okay, I'm going to use my calculator, but let me just simplify it a little bit for the sake of typing. So let's cancel out the 2's. So that's x over plus, let's see, these 2's cancel, which is okay. There's a minus sign. I think I'm going to bring the minus to the front. Come on, eraser. Okay, the minus, and I'm going to leave it 30 minus x at the top, and I'm going to leave the square root as it is because I'm just going to have to type it in my calculator anyways. Okay, now I'm going to go ahead and graph W prime, and I'm going to see where it equals to 0. And then I'm going to use that to find the critical number, and I'm going to determine whether it is a minimum or maximum. Okay, I will put a picture of my graph here in a second, but when I graph it, I can find that at x equals 9, W prime is changing from negative to positive, so it represents a relative minimum. Because it's the only critical point and it represents a relative minimum, it's actually the absolute minimum. You might have to change your window a little bit, but you're going to stare at it and see what it looks like. Now, if you did your setup a little differently, I got that X is 9. 9 is the side closest to the 12-foot tower. If you had your X over here, 30 minus 9 is 21, you would have gotten 21. They represent the same thing. Now I need to answer the question. It says, where should the stake be placed to use the least amount of wire? Okay, since I found this X, I'm going to say the stake should be 9 feet from the 12-foot tower. Okay, had you done your X's in the opposite direction or oriented your picture different, you might have the answer. The stake should be 21 feet from the 28-foot tower, and that's equally correct.